Sorry, realized I did not have the voice on. So I will repeat a bit of for you in the here, so that also the people at the watching the video can hear what I was saying. So asymptotically change spends the alpha percent of time where alpha percent of posterior mass is. But then in finite time, the initial part of the chain may be non-representative, and we may get lower error of the estimate if we remove the initial part. And you can see here the initial part sticking out from the other draws, and it's just easier to take it away, although in infinite time it would not matter. And then previously this has been called burn-in to remove one part of the initial part, and now the recommended is warm-up. And it's also because specifically in Stan, the warm-up includes also other things than just drawing the initial part to the initial value. It has also some adaptations, so the warm-up is a better name also in that name. So we remove draws from the beginning of the chain which are not representative where the most of the posterior mass is, or what's the typical set. Then the convergence diagnostics can also be used then to figure out when do we have reached the typical set, and is this Markov chain moving around the typical set fast enough? And then meaning that if it has reached the typical set and if it's moving there fast enough, then we get something which is useful as a sample from the target distribution. So if the chain has converged, then we still have also the question that how do we estimate this Monte Carlo estimate? So the expectation, this approximation of just taking the empirical average, that's still valid. But since these are not any more independent draws from the posterior, the Monte Carlo error tends to be larger than with independent draws. It can be in some specific cases also smaller than with the independent, and we'll come back to that later. So last week I talked that, okay, we can then compute these Monte Carlo standard errors and estimate how many draws we need based on how many draws we need, and now we can evaluate what's the actual effective sample size. What would be the corresponding number of independent draws given we have dependent MCMC draws. But first then the bit of these convergence diagnostics. It's very good idea to run several chains with different starting points. Here you can see different chains with different colors started at different locations, and it's easy to see that kind of they are still, these chains remember where they started. They are not mixing with each other, and as long as we can kind of tell apart these different chains, we know that, okay, this was too short run. And we just need to run longer and then remove the initial parts. We can also look at these like trace plots, so marginally, just each parameter separately. It's easy to see that there's a still trend. So from the initial points, there's a trend towards the typical set, but also that they are not mixing well. If we run much longer, now it's not anymore easy to see kind of all the chains are overlapping. It is possible to also look at these kind of trace plots, and for example, when you are doing your assignment, it's useful that you will see how, for example, changing the step size in Metropolis affects the behavior of Markov chain. But this is also that it's not easy to see from these plots whether it's actually converged, and looking at many these kind of plots for different parameters is also takes time, and it's better to have some quantified measure whether the chains are similar. So we recommend using this R-hat. In PDA3 it's called also potential scale reduction factor. But now we used just the R-hat as a shorter version. And it compares then means and variances of the chains. Here, there's 10 chains, the same as they contain these previous images. And for each chain, I've computed mean and variance. And using that mean and variance, I plotted Gaussian distribution, the blue lines. So we summarize each chain with the Gaussian distribution, and you can see that these Gaussian distributions are not completely they are not very similar. So obviously these different chains are still sampling from different parts of the parameter space. And we can compare these, so we can compute what's the width invariance. How much each chain has explored, what's the variance it's explored, and take average of that. On the other hand, we can compute what's the total variance if we combine all these chains. And we can then compare those two. So in the bottom plot, the blue dashed line is now average of these within chain variances, and so it's narrower. And there's now the var-hat plus, which is total variance estimate, which is wider. And if we then look at the ratio of these variances and take square root, we get R-hat. And we see R-hat is now larger than 1, so it's 1.64 in this case. And when it's larger than 1, we know that, okay, these chains are not yet sampling from the same part of the parameter space. We need to run them longer. If we run longer, you can see that, okay, the Gaussians start to resemble more each other. And now also the width invariance, so the average of the width invariances and the total variance estimate, they are closer. R-hat is still larger than 1. And more iterations, and now the different chains are giving more and more similar estimate for the mean and for the variance. And here now R-hat is 1. And we are saying that, okay, now we've run long enough that we have enough accuracy for the further analysis. So we have m chains, each having n rows. Now these slides are using notation in a new R-hat paper. So this is slightly different notation than in PDA3. But it's also that this notation is what is used in Stan manual, so trying to be more consistent what's the more recent material. Within change variance W, so here S squared M, it's just the variance for each chain M, where M goes to 1 to capital M. And then the W is just simply average of these variances from each chain. Between change variance is so that we compute there's theta bar dot dot, which is average of averages, so it's the total average from all the chains. And theta par dot m is the mean of each chain. And then we compute what's the variance of the means of changes. And then that's the part of this B. There's a reason why we now, instead of just computing directly like 1 per m minus n, why we want to include any here is how the later things look like. But it's also that when we are comparing these within chains and between chains variance, we have to remember that if we would just look at the variance of the means of course has less variation than the total number of draws, and how much less depends on this n, and then by multiplying by n we get back to this between chain variance estimate. So b divided by n would be the variance of the means of the chains, and b is then estimate coming from estimating that, and then like what would be the total variance estimate. And then we can combine these two things. So how we can compute the variance estimate given within and between variances is using this weighted combination of W and B. And there's a reason why it is made in this way, so that it has certain nice asymptotic properties. Now, important part here is that if we have starting points which are over this burst, then we know that if they are over this burst, then this between chain variances is overestimate, and it affects this, that this is also then overestimate. On the other hand, we know that then just the W, the within chain variances, it's underestimate, because for a single chain, when we start somewhere and it starts to move around, initially it's not move around enough, and so the within variance is less. Eventually, when n goes to infinity, then also these within variances would go to true variance. So we have now one overestimate and one underestimate, and then we divide this var hat plus, which is the overestimate, by W, which is underestimate, and then before convergence this would be then larger than 1. And we can use then this as a diagnostic. Taking a square root is just changing it to certain scale, but doesn't kind of have big effect. Just make the interpretation bit easier. So back to this demo where we had W within chain variance estimate and var hat plus, which was the total variance estimate. One is the underestimate and one is overestimate, and ratio of 10 is giving us R hat. And we can then see when the chains start to look more and more like each other. We can also say now that this R hat estimates how much the scale of some parameter could reduce if we would run these chains longer and longer. And if our sampling algorithm works correctly, then R hat eventually goes to 1 when we have infinite length chains. And if R hat is big, the new paper recommends 1.01, Previously there's been also 1.1 recommendation, but since Stan is so fast and related to kind of the overall reliability of these convergence estimates and effective sample estimates, it's actually usual that it's better to be around here, and then there's not usually much difference in time with the weight to these smaller values of r hat. We have to remember that if r hat is close to 1, it's still possible that chains have not converged. We might have the problem if we start all the chains in same point, for example, that then the var hat plus is not overestimate. It's possible that we get false results if the target distribution has actually infinite variance and r hat can't work because it was based on variance estimates, and if the variance is actually infinite, it breaks down. And also it's possible just by chance when n is finite. And we come back also then later to strongly multimodal distributions, which can be problematic. Dynamic HMC has certain problems with certain distributions and so on, so there will be additional examples later. The original r hat was from beginning in 1990s, Gell-Mann and Rubin, and there's been few variations also before PDA3. PDA3 added a split version, which improves speed of analysis in case that if we would have these initial points too close to each other and all the chains would be still moving in some same direction and not be stationary yet, and then splitting them in two parts, we get a bit more kind of the better capability of finding out possible problems with stationarity, and then we compare the means and variances of split chains, and then we kind of M is actually then, if we otherwise run 4 chains and then we split, then we have 8 half chains, and M is then 8. I already mentioned that if we get r hat 1, one reason might be that actual target distribution has infinite variance. For example, if the target distribution is Cauchy distribution. And even if the target distribution has finite mean and variance, if it's just very large variance, there can be problems. And then we came up with the solution of rank normalized r hat. So this is not in PDA3, but if you are using the most recent implementation of r hat also in your assignments, then you are using also this rank normalized version, and it's important to mention what it's doing. So by using this rank normalization, so instead of using the original parameter values, we can get these draws from these chains and compute ranks for the values, and then ranks are inverse normal transformed so that we get something which is close to normally distributed, and then comparing means and variances is again well defined. There's also in this paper additional thing in PDA3 we had splits, and now we added folding, which helps detecting scale differences between chains. And also there's local convergence diagnostic, so we can also detect if there's certain part of the parameter space where these Markov chains have problem, and I can show you examples next week. And also the paper has then how we can compute Monte Carlo standard error estimates for quantiles, which is often useful because we often report posterior intervals, and then we would not like to know how many posterior draws we need that we can report posterior interval with certain accuracy, how many digits we show there, and then we can also compute these. And the notation has been updated compared to PDA 3, and that's why also I've now showed in the slides with that new notation. So you don't need to read this whole paper. Of course, I recommend for the interest to check that. So when making your assignments, it's enough that you understand the basic part of the RHAT, comparing means and variances, and then just don't get confused if there are some changes in terminology from the new RHAT functions. Okay, there are also other convergence diagnostics than RHAT, but that's the first one you should check. Next week, when talking about HMC, there's also HMC specific diagnostics. And then the next part is then that, okay, we have a small RHAT. How do we know how many draws we need? Because there's the posterior dependency. So we can analyze this. So the posterior dependency very often in this Markov chain Monte Carlo shows that the draws nearby in time are close to each other. So we can look at this autocorrelation, how similar the draws nearby in time are. So autocorrelation function computes how correlated draws are which are apart from each other by 1 time step, or 2 time steps, or 3 time steps. And eventually it should be that the correlation gets lower and lower. And in the same way as the eventually the Markov chain forgets where was the initial point, at any point where we are, if we run long enough, it kind of forgets where it has been. And the autocorrelation is then 0. We can use then this, that how quickly this autocorrelation goes to 0. We can use it to compare efficiency of MCMC algorithms, and also we come later to different parameterizations of models which are actually the same model, plus different parameterization. Here's an example from the Metropolis, jumping in around that distribution. And we can look at the trend or the trace plot. You can see in a trace plot also that it's sometimes the kind of the it goes down and it stays for some time down, and then it goes up and stays some time up and then down. So it's not completely it's not independently jumping around. So there's some slowness in the movement. And that's the what we can see in the autocorrelation. At lag 1, so it now says either on the x-axis, I should change it to say lag, corresponding to how many time steps apart we are. With 0 lag, the correlation is 1 because it's the correlation with the exact points. And then you can see here that it takes around 40 Markov chain steps that the autocorrelation goes to 0. It tells already about something about the efficiency. So we could take here now every 40th iteration, and then these would be almost independent draws, and we would can then use that justification as last week I discussed, that how many independent draws we use. But it turns out that it's instead of just taking every 40th, we can use these all, and it's more efficient to use these all, and we just need to take into account what's the kind of the shape of this autocorrelation function to adjust what's the effective sample size. Here's another example with small steps. You can see now in the trace plot it's moving much more slowly, and then the autocorrelation is not 0 even after 100. Here's trace plot for Metropolis with big steps. You can see now that in trace plot that it's sometimes making a big step, but now it's also often staying in the same place for some time, because we are so often kind of proposing to jump somewhere where the density is much lower, and again autocorrelation function not yet 0 at 100. So this is something now that you can also, when you're doing your assignment, or you should do, is to test how the scale of the proposal distribution affects this autocorrelation function. And then kind of there are papers on how to then tune the step size so that this autocorrelation would go down as fast as possible. So how do we use then this information from the autocorrelation is that we replace, when we are computing the variance of estimation. So last week I talked about we compute the expectation. Now we denote the expectation theta bar, and then variance of that expectation estimate depends on what's the posterior variance. So sigma squared theta is the posterior variance, and then the variance of the expectation goes down when we get more and more posterior draws, and S is now the number of posterior draws. But now we need to use effective sample size, which is the total number of draws S divided by tau, and tau is now sum of these autocorrelations. And you could remember that with the better step size, the autocorrelation went down faster. Then the sum of autocorrelations would be smaller. With worse Markov chain, the autocorrelations went down slower, and then sum of autocorrelations would be bigger. And if we divide by bigger number, effective sample size is smaller. And so this tau describes how many dependent draws corresponds to one independent sample. Notation difference. So in new RHAT paper, we started to use capital S for the total number of draws, while in PDA3 it was capital N, but there was a problem now that N is often used also for the number of observations. NF is still used part of some of the interfaces, and eventually in STAN the interfaces will report actually using ESS as effective sample size. So should be less confusing with the number of observations. In PDA3 there's discussion of effective sample size, but not so much about how to compute these Monte Carlo errors, although then it was in chapter 10, and you could combine then discussion of effective sample size and Monte Carlo error estimates in chapter 10, but then these are also both discussed in the new RHAT paper. Now when we are running several chains, so this autocorrelation function, just computing for one chain, there's usually one function in different environments in R, in Python, and so on. This is some function that you can put one chain in and it gives you autocorrelations at different lags. But when we have several chains, we want to, of course, compute common autocorrelation for a certain lag. Now again, bit of changes in notation, so that now instead of t as a time, there's an n, since we had draws going from 1 to capital N. And then this notation matches now the R hat notation I had previously. So we have there rho hat nm, so we have autocorrelation at lag n for chain m, so we still can use these autocorrelation functions to compute autocorrelations for each chain separately, and then we combine them with this equation, and you recognize w and var hat plus from R hat discussion. So this approach takes into account also what if these chains are not converged yet. So only when we have converged, then this will kind of so the kind of the combining in these, when we sum these rho hats to get this sum of autocorrelations tau, this is actually taking into account that what if they are not converged, and making the tau bigger and effective sample size then smaller. So we have also the benefit of the comparing means and variances here. So it takes into account if the chains are not mixing, not converged. Also, PDA tree has a slightly different equation for how to compute this combination from several chains, but we found empirically that it's less accurate than this approach. And Stan 2.18 forward uses this equation. And also now, compared to method which would use autocorrelation only from single chain, the multi-chain estimate has smaller variance, and it quartz form that what if these chains are not actually converged yet at all. So then we have the term sum of autocorrelations. Theoretically, that sum of autocorrelations would that we would sum autocorrelations from lag 1 to infinity. But we are not able to compute these empirical autocorrelations, these autocorrelation estimates to infinity. We have only the length of n chains, so the maximum lag is n-1, where we can compute, and even that is very, very noisy. So it's better that we truncate this estimate. So we have some truncation point and compute some these empirical autocorrelations up to a certain time point. And then the question is, how do we choose this specific time point? You can also see here now that actually why there's this 1 plus 2 and then the sum. It's because we are, when computing this tau, we are actually computing this autocorrelation. So 1 is for the lag 0, and then we are summing the lags from to 1, 2, 3, 4, and so on, but also -1, -2. So that's why we have double of these things. It's also important to know that since we have anyway finite number of draws, the tau hat in a way that if it's very large compared to total number of draws or length of the chains, we get unreliable estimates for these. So it's possible to find out this truncation adaptively. I'll just now go that if the odd and even lag autocorrelations, they have to be positive, and if we look at them, for example here, we could then decide that we can stop around 40. I skip this a bit faster. And then we have the effective sample size, ESS, or S subscript EFF, is total number of draws divided by tau hat. Some examples. The same Metropolis examples. The first one where the autocorrelation went down around 40. Tau hat is 24. And so we need to divide S by 24, which is anyway better than if we would take only every 40th draw. So that's the additional efficiency, that we use all the draws. If we would take every 40th, we would have S divided by 40. There's the one with very small step. Tau hat is larger than 100. The one with the big step, we have tau at 63. And so the one step size was clearly the better. Since it's over 4, I come to these problematic distributions next week. And also next week, Hamilton and Monte Carlo. And the reason why we use it is that it often has tau hat very small, and actually it can have sometimes tau hat which is less than 1. We can have super efficiency with the dynamic HMC implementation in STAN, so that it's actually more efficient than independent draws. And which can be also come straightly, just that it's possible that these odd lag autocorrelations can be negative if we are jumping kind of on the other side of the distribution more likely than nearby where we already are. And then there's further diagnostics coming next week, specific for HMC. Okay, stopping already over time.